cook-off. And so now, with the award for the shortest title of the session, Sam Levang with Flexible Vectorization in Xarray Using JAX.
Thank you. Yeah, so I'm Sam Levang. I'm here from a startup company called Salient that focuses on S2S forecasting and modeling. And I'm going to talk about a very general computational pattern we've been using across a lot of different applications, which is basically speeding up custom sort of algorithms and code in Xarray using JAX. The basic context here being that usually computation with climate data, especially model data, reanalysis data, gridded products, involves lots of very repetitive sort of operations over some batch dimension that might be grid points, lat long. With forecast data, you might have a big hindcast data set that has initialization, dates, lead times, etc. And the more we can push those sort of repetitive operations down to low-level matrix operations, the faster your code is going to run, instead of loopy vector sort of products, which are extremely slow in Python. So the proposal I'm putting out here is basically JAX is a great tool to accelerate all kinds of these sort of workloads without ever having to leave Python. Anything you can write in NumPy, you can write in JAX and make it really fast. And this works for pretty much anything on the spectrum of scientific compute operations to ML, which I'll describe a little more in a second. And just to set expectations, I don't have some shiny open source package around this yet. This is just going to be some really simple code examples and discussion of how we've been using this. Okay, Xarray, probably everyone here knows it well. Tagline is Xarray makes working with labeled multi-dimensional arrays in Python simple, efficient, and fun. I totally agree. I'll leave it there. I try to stay in Xarray whenever I can, and it prevents me from making all kinds of mistakes that I would otherwise make in code. JAX, I'm guessing people are less familiar with in this room. Maybe some of you have heard of it, played with it a little bit. The tagline is JAX is AutoGrad and XLA brought together for high-performance numerical computing. That's a bit jargony. What it comes down to is you can make anything that you can write in NumPy really fast with JAX through a few convenient transformations. So what JAX does is re-implements the entire NumPy API plus a bunch of SciPy and other core Python compute libraries in a way that everything is differentiable, which means you can apply this grad transformation and you get to any function and you get another function that is the gradient of that function. So super flexible for any sort of application that involves ML, optimization, etc. Beyond differentiability, what it does is compiles all of your code down to really fast kernels using XLA, which is Google's accelerated linear algebra compiler. Pretty much all automatic. You don't really have to think much about how you write it, and it'll make it fast. You do that just through these few key transformations on functions, which I'm going to mostly focus on VMAP today with the context of having lots of climate data points we want to map over. That's vectorization, but these others are super useful too. And it works seamlessly across all compute types, CPU, GPU, TPU. So I don't think JAX is like offering totally new features necessarily, just as a comparison to what else is out there. We've seen people talking about Numba and TensorFlow PyTorch today already. Numba is super common and well understood for speeding up scientific compute sort of operations in Python. It's good for vectorization and making loopy code faster with JIT compilation, but it doesn't really do differentiation yet. So you can't take gradients, and it doesn't work for ML type applications. Then on the other hand, you have the heavy hitters of ML, TensorFlow PyTorch, that do have nice autodiff frameworks. They kind of work for other scientific compute applications too, but they're really made for building deep learning models. So they're not, it's kind of clunky to try and port over stuff you're doing in NumPy to work with TensorFlow and PyTorch. So JAX kind of does it all in one, and I think that's what makes it really nice. Okay, I'll move on to just a couple very simple, somewhat contrived examples of how you can use this with gridded climate data and how we're using it. The first being more on the simple scientific compute side of things, which is just trying to vectorize an existing NumPy method that works great for 1D arrays, but is slow for gridded data, or doesn't work at all for gridded data, actually, for NumPy. So the example here is interpolating between pressure and height coordinates. So you have, for example, model data that's on levels. You have an array of the height field on those levels and maybe temperature as well. You want to interpolate the temperature to some consistent height, for example. If we look at the NumPy docs for interp, you see right away that the interpolation coordinates and data are expected to be 1D sequences. So this doesn't really work for gridded data. You can make a nice little workaround with Xarray, use apply ufunc, which is kind of the all-purpose wrapper for anything that doesn't exist in the core API. You can set your core dimensions to be interpolation along the levels onto the height coordinates. The problem is that because this only takes 1D sequences, the interp function of NumPy, we have to set the vectorize option to true, which makes this pretty slow because it's basically converting your code to a bunch of slow Python loops over grid points. So works fine for a small data set. This is just a single slice of the atmosphere I pulled here. Takes 3 seconds, so not great. In JAX, you can rewrite a vectorized version of this in just a few lines, which comes down to taking the JAX NumPy equivalent interp function. And the way I'll usually do this is to handle unknown array sizes. You might have multiple dimensions. You can just do a nested VMAP transformation over each one of the batch axes. So anything that's not the core interpolation dimension, you can take transformations of transformations in JAX. And we just pass this to apply ufunc the same as our previous version, except this can handle an array of any shape, any number of dimensions. It doesn't have to be one-dimensional. So we can turn off the vectorize option, and it's way faster. We get about 20 times speed up just on this small data set. You can, of course, do this in Numba too, for people who are familiar with Numba. It's pretty similar, a little different syntax. Performance came out similar. I wouldn't put too much stock in how those numbers compare. This is just CPU code. And so yeah, I'm not proposing this is super novel or anything, but just to show that JAX can basically swap in for most things you would do in Numba to speed up otherwise slow Python code. Okay, here's a second example that is also simple, straightforward, but I think gets closer to the real unique capabilities of JAX, which involves gradients. So this is just a simple optimization problem. Let's say we have a big temperature array and we want to fit some seasonal cycle to the data at every point with a sinusoid with enough parameters to appropriately capture the shape. I picked this example because Xarray already has a curve fitting API that I worked on, so I know it fairly well. And it just uses SciPy's curve fit under the hood, which is, again, only takes one-dimensional arrays. So we have to pass it through apply ufunc and turn on the vectorize option, which makes it really slow when you have big gridded data. I scaled up the data set for this profile to 1.5 gigs. And because it's doing an optimization loop and has tons of points, it takes 15 minutes just to fit this simple sinusoid to a bunch of points, which you can speed up a bit with Dask parallelization, but only so much because the underlying operations are still pretty inefficient. In JAX, we can rework this again. The vectorization piece is very similar, just a VMAP over all of the batch dimensions. I had to get a little creative on the optimization piece for this because something I learned by trial and error really is that More traditional, like second order optimization methods don't seem to work very well with VMAP because you have some inner loop happening that doesn't match between the different points. So actually here I'm using a more traditional deep learning solver, an atom optimizer first order method, which does batch very well. Just convert our curve fit to a RMSE loss type function. And yeah, this is not even something you would think would be efficient in terms of the optimization algorithm, but because you can batch it all together, I ran this on a GPU, get it done in 5 seconds. So a couple hundred times speed up, which is pretty cool. Just a few final points to make that, especially with the interplay with Dask, it actually works quite well, this pattern, because one, JAX functions release the global interpreter lock, so you can get really good performance across CPU cores just by chunking your array and using the default threaded scheduler with Dask. It also works great for really large arrays that you want to run on GPU but don't necessarily fit, because you can chunk your array and pass chunk by let apply ufunc in the Dask scheduler pass chunk by chunk to the GPU, and you don't have to worry about running out of GPU memory, which is always an issue. And there's plenty of challenges too. JAX is just kind of hard to learn because it's different than your typical Python programming model. Assumes a very functional programming model that takes a little time to get used to. Yeah, so these are examples of how we're basically going from Xarray space backed by NumPy or Dask arrays, moving into JAX for a minute to speed up a computation, and then back to Xarray with another, you get a NumPy array back out. Kind of raises the question, couldn't we just have JAX array as a duck type for Xarrays? Complete the end-to-end integration that way, which is actually closer than I realized. I've found a few issues working here. JAX is very close to implementing the array API standard. There's a couple outstanding issues and some trickery and handling that will have to happen about coordinates because indexing probably won't really work with JAX arrays. And then another thing I found just in making this presentation is that actually the open source GraphCast library has an entire Xarray JAX wrapper, which is a little hacky and has some workarounds and is unsupported, et cetera, but with that, you can basically do this now, take an Xarray data set and back it by JAX arrays. So that's really cool. I hope all this end-to-end integration keeps moving. If you're able to contribute there, please do. In the meantime, these are just some examples of how you can kind of work around by moving into JAX temporarily to speed up some of these computations. And I think it's a pretty cool pattern, so especially for ML stuff. Thanks. Questions?
Thank you, Sam. We have plenty of time for questions. Ryan, you want to? Yeah. And I think this is the last talk in the session as well, so we have 15 more minutes in here, so also feel free to ask the questions for any of our speakers as well.
Amazing talk, Sam. Just wanted to get a quick clarification on some of the performance comparisons you showed. You mentioned like there's a couple things that are happening. One is like the vectorization and then the other is GPU. So can you help us disentangle in the comparisons you showed, like how much of that is the vectorization versus moving it to the GPU? Can JAX just run on CPU and use multi-threading internally? Does that work well today?
That does work well. I think the answer is it depends. Like certain operations that are really matrix multiplication heavy, like optimization loops, just perform really well on GPU. That's just like a natural design aspect. But yeah, we found it to work great on CPU too for a lot of these cases. Like vectorization is a big part of speeding up what would otherwise be Python loops. So yeah. And like you said, you can use it with a threaded scheduler, which is nice and fast.
Just to follow up on that, like why would you help me understand why you would use both Dask multi-threading and JAX multi-threading? Why do we need Dask then if you
Sure. I'm not an expert in JAX, but as I understand, mostly JAX code will run single-threaded on CPU cores unless you explicitly T-map it over multiple CPU cores. Yeah, I don't totally understand how that works, but that's been the easiest way I've found, is just use Dask scheduler to do it.
There aren't immediate questions in the room. I want to ask a question. So, Sam, in a lot of your examples, you JITted. You're kind of like the heavy lifting loop, which has the advantage that JAX is going to trace through and do all the fusions and kind of reduce stuff. But I just want to call out on this slide here, like a future development is just dropping in JAX as a replacement for a NumPy array. Could you comment at all on your experience of just without even using JITting or any of the fancy machinery there for acceleration? Do you see any performance speedups or changes in ease of use if you simply just use the JAX array, so that rather than use your the BLAST or whatever numerics library is compiled in your system, you get all the fanciness of XLA, which is the modern version of those same linear algebra computations?
What I've seen and what I think the JAX people say is we don't actually expect that to be any faster. NumPy is pretty well optimized with loss and stuff. So I think without using these transformations in an appropriate way, you don't usually expect much speed up. Yeah, that's been my experience, at least.
Any other questions from the room? And again, we still have about 10 or so minutes left to close up the session. So any additional questions for Sam or any of our other speakers are more than welcome.
Have you experienced any, as far as looking at speed ups and comparisons? I mean, I've been starting to use JAX-Opt, and particularly for some of my wind retrieval software, and I've noticed that JAX-Opt and the SciPy seem to have about the same performance in terms of speed, at least on a regular CPU. Have you found JAX-Opt to be advantageous over the regular SciPy optimization packages?
Yeah, I've found JAX-Opt to be a little hard to use myself, actually. And one part of that is something I mentioned earlier, is that it seems like the second order methods, which are mostly what SciPy's optimization routines use, just don't work well with VMAP. I don't understand all the details. But what I have found is moving to the first order type stochastic gradient descent type methods, those do work really well, and they're clean in JAX-Opt. You can use the OptAX solver and get really good performance on those.
Yeah, sure, Max.
Yeah, so I know a lot of the talks in the session talked about sort of ways of optimizing and using some of these open source tools to do that. Do you think there's an opportunity to, I know Pythia was brought up earlier about creating a cookbook. Do you think there's an opportunity then to create some sort of performance-based cookbook, sort of using some of these examples or documenting some of the best practices or some of the example workflows here? Because I know a couple of talks didn't necessarily say they want to create a new package, but more so show how to leverage some of the different pieces within the ecosystem to really improve performance.
Yeah, I think that's a good approach as far as JAX goes. Like I said here, I'm not sure this is really worthy of a standalone package. It's great for custom kind of one-off stuff, but like much of the NumPy API does actually work great with ND arrays. You don't really need this vectorization layer on top of it. It's more these kind of custom algorithms that it's really good for. So I think, yeah, documenting some examples, making it more accessible in the community would be a good approach for sure.
Maybe to extend that question to JT Kelton and Robert, do you all have any perspectives on contributing workbooks or other resources back to Pythia? And feel free to hop up on the microphone if you have thoughts.
Pretty short answer, but enthusiastically yes.
Also yes, and the GitHub repository has some working examples for some of the things and features, including working with gridded data, or that's, if it's not already in there, it's coming. So there's some of that, but cookbooks sound like a good.
Also, yes.
Awesome,
That's what we like to hear.
awesome. Yeah. Maybe one other question. I'm just kind of interested in an interaction between Kelton and Sam now. So Kelton, you made a defense of C++ as your language of choice, and I think you had some really good and compelling reasons on why that's the right design choice for your library. Seeing JAX and being familiar with some of the other tooling, are you rethinking anything, or what would be your reservations towards jumping into using JAX as the foundation of your library?
So the main thing is my employers have certain restrictions on what we can and cannot use. And
That's
so
a big, yeah.
unfortunately, like as much as I am a nerd and love the bleeding edge stuff, I have to think about what can we use in our systems now and what's going to be around when I'm not here and what's going to be maintainable by the person who replaces me. And I have a little bit of distrust in some of the more ecosystems like this, where I don't know how long that support is going to exist for. And so I've had to approach vectorization and chunking and performance from a hardware level and cache line locality level and all that sort of stuff, which is why C++ ended up being the one. So really it's that I know that since we're using Fortran now, we're going to be using C++ in 30 years and the computers will still be running it.
We'll be using Rust.
We're using Rust.
Yeah.
Rust is a tad more difficult than anything we've seen today. That's a good point. No, I thought that as much as that, often there's requirements beyond just, the ease of coding and fanciness. There's institutional requirements that are much more brittle than the software itself.
And Rust is very interesting, but it's not the same issue right now. I don't have compilers where I can ship onto it. Have to change the scope a little bit to what you can use.
Any last questions before we wrap it up? And Julie and I can share the advertisement for the next iteration in the session as well. We can pull that up. Just ask a question so we can pull it up on our computers and advertise it. I can just read it off on mine if so.
Okay. I believe we're in this room all day, so don't get lost.
Yep. Yeah, so looking at up here, so we have a coffee break now until 10:45, and please join us again here. At 10:45, Scott and Jingying will be chairing a session on teaching, training, outreach, and building communities around open science. So we hope to see you all there in a little bit under an hour.